All right, we're going to pick up where we left off last time. The discussion for today is all going to be about preparation of alcohols. And for these first sets of reactions, we're going to be starting out with an alkene and doing a hydration reaction. Okay, so if we look here, what happens to our alkene? We have that carbon-carbon double bond. That double bond gets broken. On one side, we're going to stick our hydrogen from water. And on the other side, we're going to stick the OH, that hydroxyl group, from water. All right, so we're going to be looking at various reagents for these hydration reactions. It turns out that if you just mix an alkene with water together, there's no reaction that occurs on any sort of a reasonable time scale at least. So you always got to catalyze these reactions. All right, so our first one is going to be our acid catalyzed hydration. All right, importantly, we're going to learn 3 of them in this lecture here, these hydration reactions. This one we want to put a little bit of an asterisk next to, because this one we're going to study the mechanism for as well. The other ones are going to be kind of left a mystery. We'll talk about the results. This is the one where we know that those details in the middle. All right, so let's just do butene. We have a 4-carbon alkene here. All right, this uses dilute sulfuric acid. So we're going to put H2SO4 and water. Okay. All right, so the first step in our mechanism here, let's kind of leave that for our substrate reagent product combination. We'll do our mechanism down here. All right, in this first step, we have our double bond playing the role of a nucleophile, like it does so often, right? So that pair of electrons there is glowing red hot. We got a lot of electron density at that pi bond. All right, and the first step is going to react with that sulfuric acid. You'll see this one of 2 ways, either the actual sulfuric acid or hydronium. All right, and hydronium is actually a little bit more accurate because as soon as you stick sulfuric acid into water, that proton's going to dissociate off and to a hydronium ion here. All right, so you'll see either of these. I don't really care for the exam, but that's my logic of why I'm going to be using hydronium here as my source of proton. All right, and that proton is left relatively electron deficient, right? So in our mind's eye, that's what's cold here, what's glowing blue. And that double bond is going to reach out and accept that proton. Oh, whoops, just one. All right, so then everybody take a second and draw me my intermediate here for this first step in our mechanism. All right, so I have my 4 carbons. All right, that double bond is gone. I have a new bond with hydrogen. But the question is, which hydrogen, or which carbon rather, is hydrogen going to go on? The orange or the green? All right, which side of the double bond accepts that hydrogen? Well, importantly, the key here is what happens to the other carbon, right? If I put a hydrogen on one of those carbons, what's the other one going to become? A carbocation, right? And so that's the key here is where does that carbocation want to form? It wants to form on that more substituted carbon. So that means hydrogen is going to go on the less substituted carbon. All right, so we have this carbocation intermediate. Where does that carbocation form? On that more substituted carbon. All right, so then the next step in our mechanism is going to involve water. All right, I'm going to give you the product of this next step. Okay. We have a new bond between carbon and oxygen. I need y'all to fill in my missing electron pushing arrows. I'm going to draw these bonds explicitly here. All right, take me from A to B here with my missing electron pushing arrows. I guess it'll be good to include this hydrogen. All right, so I need to draw this new bond, right? Play the spot the difference game. I have a new bond here. I need a new bond between oxygen and that orange carbon. All right, the question is, do I have my electron pushing arrow start at that lone pair and end at that carbocation? Or do I have it start at the carbocation and end at that oxygen? Which one of these is correct, red or orange? Red, right? So we have to start our electron pushing arrows at a pair of electrons and end it at an atom. All right? So we have to start our pair of electrons at that lone pair and end at that carbon that's accepting that pair of electrons. And then we're almost there. Our final product here going to be that alcohol. I'll explicitly draw in that new carbon-hydrogen bond, although you could leave it out. Oops. Right, so if we play that spot the difference game, I'm going to need to get rid of this hydrogen here on my oxygen. Okay. So this is a proton transfer. It's not just going to go flying off into space. We'll always have some base in this mixture that accepts that proton. All right. Importantly, for this aqueous acid mixture, we can't use hydroxide, right? That's a good base. That's everybody's go-to base. What's the problem with that considering my reaction mixture here? These are acidic conditions. Hydroxide's not going to be floating around anywhere, right? If we put hydroxide in there, it would immediately react with our acid. We can't have this strong base in these acidic conditions, all right? We're going to talk a lot more about conditions as we move on in this semester, but yeah, bottom line is hydroxide, yes, a very strong base, no way can exist in this world here, in this mechanism, all right? So what are we going to use as our base? We're going to just use neutral water. All right, so everybody take a second. If that's my base, get me from A to B here. Put in those electron pushing arrows to complete our reaction mechanism. I will say, just for the sake of completeness here, we do reform our acid catalyst, so we also have this hydronium ion as well. All right, so I need to get rid of this hydrogen. It's going to be my water's oxygen that accepts it. So again, I'm going to start my arrow at a pair of electrons and end it at that hydrogen atom. All right, I'm not done yet. I formed a new bond with that pair of electrons. I still need to break this bond here. So I need another pair of electrons, or another arrow representing that pair of electrons that jumps from that oxygen, or from that bond onto that oxygen atom. I will be good. I should have had a lone pair on here as well. All right, but that's how my product has these two lone pairs. Where did this one come from? It was that pair of electrons in that hydrogen-oxygen bond. Okay. Now, I included this hydronium ion for the sake of completeness so that hopefully it was a little easier to see how we got from A to B here. But generally speaking, we do not include inorganic products in our reaction schemes, in our chemical equations in organic chemistry. We just get real lazy about it. All right, so my final, again, just kind of summarizing here for this reaction. We got our mechanism. My product would be, we know how to name it now, 2-butanol. All right, so in addition to this reaction being one that we know the mechanism for, we also want to keep in mind what we call the regioselectivity, meaning that that oxygen goes on a very specific region of that product. We call this a Markovnikov, meaning it goes on the more substituted carbon. All right. Now, one result of us knowing this mechanism and specifically knowing that it goes through this carbocation intermediate is carbocation intermediates are kind of a pain in the butt. All right. Anytime we have a reaction that goes through a carbocation intermediate, we got to watch out for shifts. All right. For those methyl and hydride shifts. Okay, so our first hydration reaction is this acid-catalyzed hydration reaction. We have a mechanism here. First step is our electron-dense pi bond attacks that proton of our acid, forming that carbocation intermediate. Water is then going to play the role of a nucleophile here and attack that electrophilic carbocation. And then we have one last deprotonation step in order to get our alcohol product here. Okay? Because that carbocation intermediate, we have this regioselectivity where the oxygen is going to go on the more substituted carbon. And because of that carbocation intermediate, we also have to watch out for hydride and methyl shifts depending on the structure of our reactant. All right, we got another one. This is what's called an oxymercuration reaction. right, if we take our same 1-butene, all right, now we're going to react it with this substrate of mercury acetate, HgOAC2, and water. All right, that's going to be our first step. And then we follow that up with this reducing agent, sodium borohydride. All right, so this is our list of reagents here. I'm not going to, as previously, you're not going to be asked to sort of memorize reagents. You do need to spot recognize them, right? So the more we learn reactions, the harder it is to fit everything in your brain. A great way to do it is to use flashcards, because you just need to be able to spy what it is that this thing is doing here, okay? And that mercury in our oxymercuration reaction is a pretty rare transition metal to have in our set of reagents. All right, we'll see sodium borohydrate. You see acid formulas a lot, right? So you want that one little key that stands out that makes it a unique list of reagents. Again, that mercury is very, very rare as far as reagents go. So I'm going to tie that in my mind to an oxymercuration reaction. We don't have any mechanism for this one, all right? I'm just going to give you the products here. Okay. In this case, we would get that exact same 2-butanol, because much like our acid-catalyzed hydration reactions, our regioselectivity here is that it is also a Markovnikov reaction. It will also put that OH group on that more substituted carbon. Okay, and again, we don't know our mechanism, but I will tell you we know enough that the big difference between this and our acid-catalyzed hydration reaction is that there are no shifts. This reaction does not proceed through that carbocation intermediate. You have no chance for any sort of an internal rearrangement occurring. That's why it's sometimes preferable over just a simple acid-catalyzed reaction. All right, as far as like practical reagents go, sulfuric acid and water is just about as cheap as you can possibly get. All right, the problem is that those mechanisms that have carbocation intermediates, they can do some crazy stuff, including those hydride and methyl shifts. So that's maybe why you want to break the bank and spend it on some oxymercuration reaction here using these more expensive reagents, because then you don't have that high energy intermediate. You don't have that same worry about these rearrangements that can occur. All right. We got one more. This is what's called a hydroboronation reaction. All right. We're going to start out with our same substrate. Oops. All right. Now we're going to, again, we got kind of a fancy list of reagents here. Use what's called borane, BH3, in tetrahydrofuran, just a special solvent that you need for this reaction. And then you follow that up with hydrogen peroxide and base. All right, this is going to be a hydration reaction, right? Same category. Again, we need to be able to spy our reagents here. And the thing that kind of jumps out to me is boron, we don't see a whole lot, BH3, right? And so it turns out that this borane's claim to fame here is that it's going to put an OH on this molecule, but specifically on the less substituted carbon. All right, so again, we don't know our mechanism here. We're not going to take a look at a mechanism, but we know enough to know that this has this regioselectivity we call anti-Markovnikov. Meaning that the OH is going to go on the less substituted carbon. All right. And again, we don't know the mechanism, but we do know enough to say there are no hydride shifts or methyl shifts that can occur. No internal rearrangements that we're worried about for this one. Cool. All right, so let's summarize. Let's just make a little summary wheel here. We're going to put an alkene in the middle. And we're going to draw our product for each of these hydration reactions. All right, so in each of these, we're going to get an alcohol product. That was the name of the game, preparation of alcohols. The question really is, which side of that double bond, orange or green, for our oxymercuration reaction, which one is it going to be, orange or green? It'll be that more substituted orange carbon. And for my hydroboronation, which one is it going to be? That less substituted green carbon. And for my acid catalyzed, which one is it going to be, orange or green? Neither. Trick question. All right, awesome, cool. So importantly, why is it going to be neither? Well, remember, we have to form that carbocation intermediate. Where's our carbocation going to form? On the orange or the green carbon? Orange. On that more substituted orange carbon. And that's living right next door to an even more substituted carbon. So we're going to have a hydride shift occur, right? The hydrogen from that more substituted carbon jump ship. And so really our more stable intermediate that's going to form is going to be that tertiary carbocation, which will lead to our tertiary alcohol. Cool. All right, so all that to kind of say, watch out for the shifts. All right, in this example, we had a hydride shift occur, which is why we have this different product, where it's on neither the green nor the orange carbon. All right, so this is a good set of, or rather a good substrate to choose to kind of illustrate the differences between these various reagents. All right, the top ones, we don't have to worry about any shifts. We just have to keep in mind the regioselectivity of these reactions. Our mercury oxymercuration reaction is Markovnikov. Our boron hydroboronation reaction is anti-Markovnikov. Our hydration reactions, our acid catalyzed hydration reactions, are Markovnikov, but we have to watch out for the hydride shifts. All right, cool. So the last half here, what we're going to do is introduce a new type of reaction, what's called a Grignard reaction. All right, this is in our preparation of alcohols section, so we're going to get an alcohol product. All right, but importantly, Grignards are kind of special. We don't have terribly many reactions that create new carbon-carbon bonds, and Grignard is one that does. All right, and not only does it create a new carbon-carbon bond, but it's like incredibly flexible as well. It turns out that your substrates that you use in a Grignard reaction, there's not a terribly large amount of limitations on what you can choose, which makes it a very powerful reaction for creating molecules in organic chemistry. It also makes it kind of a pain in the butt from a student perspective, because anytime we're creating new carbon-carbon bonds, that means the product that we get on the other side is going to be bigger than the one that we started with, than our substrates, right? So we're going to grow our molecule, and we got to make sure that we're keeping track of what carbons are what here. You know, it's kind of easy enough when we're swapping out a functional group. It's a little bit harder when we're creating new carbon-carbon bonds, because then our molecule's getting bigger in this reaction, right? So we just got to be a little bit more careful about keeping track of things. Okay, so before we take a look at the actual reaction here, we need to introduce what's called a Grignard reagent. These are the reagents used in this lab, in this experiment. Okay, it turns out that if you take an alkyl bromide and you mix it with magnesium, just straight up magnesium metal, little metal shavings you put into your reaction mixture here. That magnesium is going to magically insert itself in between the carbon and the halogen. Right, so now we'll have magnesium and then our halogen. And this thing over here is what we call a Grignard reagent. So we're going to take this thing and react it with another molecule. All right, something everybody's organic chemistry brain should have just exploded a little bit, because where does magnesium live on our periodic table? Metal or non-metal? It's a metal, and we don't talk about metals in organic chemistry, right? We definitely don't talk about metals with covalent bonds. So this is our first introduction to this new category of molecule that is really powerful in organic chemistry, called an organometallic compound, meaning an organic molecule that also contains a metal in there. All right, so then what is this Grignard reagent doing for us? Okay. All right, well, if we zoom in here, carbon we don't really think about as being a very electronegative element, right? That's because we're always comparing it to all the other non-metals in the world. Compared to the halogens and oxygen and nitrogen, carbon's the least electronegative of all of them, okay? But now we're comparing carbon not to a non-metal, but to one of our metals, something on the exact opposite side of the periodic table. Metals' electronegativity is crap, right? Metals don't hold on to their electrons very tightly at all. So in this bond here, our carbon has a ton of electron density. This is a very polar bond where carbon is the one holding all that electron density, and that metal, that magnesium, is left relatively electron deficient. So much so that sometimes you will see these Grignard reagents drawn in resonance with a carbanion salt form here, right? So I mean my carbon now has a net negative charge and is ionically bonded to that magnesium bromide. All right, so if that carbon atom has a ton of electron density, is that going to make it a nucleophile or an electrophile? Which one is our electron-rich species? All right, look, I'm going to ask you this question 100 times this semester. By the end of the semester, if you can't answer it, I can't pass you through Organic Chemistry 2. It is the basis of all chemical reactions in organic chemistry. Something electron-rich is reacting with something electron-poor, right? That's our basis for all of our reactions. All right, our electron-rich species is our nucleophile, and that's kind of the whole shtick of a Grignard reagent, is we have this nucleophilic carbon atom. Grignards are going to play the role of nucleophiles in our chemical reactions, and it's specifically that carbon atom that is going to be that nucleophile. Okay, cool. So we got our reagent here. Now let's take a look at an actual reaction. We're going to use this guy and react it with another organic substrate here. Okay. we're going to start, we're actually going to bring Grignards up quite a lot throughout the course of this semester. The first reagent that or rather substrate that we're going to talk about with Grignards are aldehydes or ketones, all right? Our carbonyl containing compounds are going to be our first Grignard substrates. All right, so let's take this thing and react it with that Grignard that we just created. All right, again, we're going to create a new carbon-carbon bond in this reaction. So what two carbons are we going to be linking together here? All right, we have that nucleophilic carbon in our Grignard. Right, ton of electron density on that carbon, so it's glowing red hot. That is going to react with the electrophilic carbon in our carbonyl bond here. Another thing you're going to hear me say over and over and over again, especially when we start talking about carbonyl compounds, is this electrophilic carbonyl carbon, all right? In a carbonyl bond, that oxygen is pulling all that electron density away from that carbon atom, leaving that carbon atom relatively electron deficient, right? So our electrophile is that carbonyl carbon. Our nucleophile is that Grignard carbon. And specifically the one that's bound to that magnesium atom. All right, so when I draw my products here, I'm going to start out with these 4 carbons from my original substrate, from my carbonyl compound, from my aldehyde. All right, so just keeping track of who's who. 1, 2, 3, 4 carbons. That's these 4 here. I'm going to draw my new carbon-carbon bond. What lives on the other side of that new carbon-carbon bond? It's got to be that red carbon from my Grignard. All right, and then I need to add my Grignard also wasn't just 1 carbon, but had 3 carbons. I'm going to add those remaining 2 that I need. Okay. Lastly, our oxygen from our aldehyde here, it did not just fly off into space. It is still located on that formerly carbonyl carbon. It's just now it's not a carbon-oxygen double bond. It is a carbon-oxygen single bond, or our alcohol product. All right, so we have our new carbon-carbon bond, and we now have an OH on what used to be that carbonyl carbon. Okay, one thing that's always a good idea when you're doing your reactions, but is especially important on reactions where you're creating new carbon-carbon bonds, where you're growing your molecule, is counting carbons, right? Make sure you got the same number of carbons on the left as you have on the right. You'll see me up here like tapping my page all the time. I'm making sure I've kept track of my carbons correctly, right? So I need 1, 2, 3, 4, 5, 6, 7 in my product. 1, 2, 3, 4, 5, 6, 7. And I even color-coded them here so I can make sure to keep track of who's who. All right, so before we move on, we'll discuss this a little bit in more detail. Let's kind of make sure we got the basics down here. All right, I want everybody to take a second and tell me what's going to happen if we react acetone. with a 2-carbon Grignard reagent, right? Let's try to predict the products of this reaction here. Alright, so I'm going to start by figuring out where my new bond should be, between which 2 carbons, right? Going to be between my carbonyl carbon, my electrophile, and my Grignard carbon, specifically the one bound to that to that magnesium. So then when I draw my product, I'm going to start with those 1, 2, 3 carbons from my electrophile. It's that middle carbon that's playing the role of my electrophile here. So when I draw my new carbon-carbon bond on the other side, is going to be that red carbon, right? And then I need to include, I made sure to include 1, 2, 3 carbons from my electrophile. My nucleophile had these 2, so I need 1 more. All right, and then lastly, we don't want to forget our functional group. We have to have an alcohol product. Where does that OH go? Again, on that formerly carbonyl carbon, our blue carbon. That's how we get our alcohol. All right, cool. So, Grignard reactions. We're actually going to take a look at a mechanism for. All right, we've already kind of talked through it a little bit. Let's start out with our electrophile. And our Grignard reagent. All right, we said that the electrophile was which one? The one on the left or the one on the right? Left. Our electrophilic carbonyl carbon. And that carbon in our Grignard had all that electron density. It's glowing red here, okay? So we're going to have nucleophilic attack. Our nucleophile is going to attack our electrophile, all right? Now, real quick, what's the problem with this arrow here? The base of it is at my nucleophile, all right? That's cool. The head of it is at that electrophile. That's cool. I got a problem here, though. Yes, that is definitely a problem, and we will resolve that here in a second. There's another problem, though, with the base of that arrow. I can't, it's atom to atom, exactly. I can't start my, my arrow at an atom. It has to be at a pair of electrons, all right? This is the biggest mistake that I see in Grignard reaction mechanisms is people drawing their arrow like this. My arrow has to start at a pair of reactions. It's this pair of electrons here in that carbon-magnesium bond that actually does my attacking, right? That's my location of the start of my arrow, Okay, but absolutely, now we have another problem. Our carbonyl carbon has too many bonds. One of the things that makes carbonyl carbons such good electrophiles is that they can accept pairs of electrons without breaking their octet, because it's just going to kick this pair of electrons up onto that oxygen atom. All right, this sequence of events of some nucleophile attacking a carbonyl carbon and that pi bond being kicked up onto that oxygen, we're going to see that over and over and over again in our mechanisms. All right, so carbonyl carbons, great electrophiles because they can accept pairs of electrons and they kick that pi bond up onto that oxygen. So everybody take a second and draw me my intermediate for this reaction here. All right, so I'm going to redraw that electrophile. I got my 4 carbons. This blue carbon here has a new bond, a new carbon-carbon bond to this red carbon. So now I need to include those other 2 from my nucleophile. All right, when we were doing our products, we had an alcohol group on that blue carbon, on my carbonyl carbon. But according to my mechanism, I'm not quite there yet, right? What does my oxygen look like in this intermediate? What's it missing? A negative charge. Right? It accepted that pair of electrons, so now it has 3 lone pairs. So I have this alkoxide ion intermediate here, this oxygen with a negative charge. Okay? So I've kind of been lying to you up until this point. There's a second step in our Grignard reactions. If we were being good with our reagent list here, we would say first, Grignard. Second, you treat what they call an acidic workup. You treat it with a weak acid. All right, so we should have a second reagent here, a second step, where we add in some weak acid, specifically to protonate that alkoxide ion. All right, so now we're ready to move on to that second step. So now I'm going to have some hydronium floating around in this solution. And everybody's going to take a second and draw in the missing electron pushing arrows to get me to that alcohol product. Or I'm going to do it because we're out of time. That pair of electrons on that oxygen attacks that hydrogen from my hydronium, creating that new oxygen-hydrogen bond. Cool. All right, we will pick up with this next class period. We're going to talk about Grignards a little bit more, and then we'll move on to some other reactions of alcohols. Yeah.
For the nucleophilic carbon, are we able to draw it just with the lone pairs? Or
That is an acceptable way on your homework. It will expect the Grignard, the more stable of the two. Yeah, okay. The more stable resonance contributor, which would be with that bond there.
Okay.
Yep.
For the questions for the interview, is there like a template or anything, or do we
Yeah.
just like?
If you go on if you open that interview assignment, there's a little page that you download.
Okay. All right.
Yep.
Yeah, I had a question about that too.
Yeah.
Do we need to have one person per career that interview?
No. Just you just need one interview coach.